Well, good day, ladies and gentlemen. My name is Mike DeVito, and I'm Director of Consumables Product Planning at PerkinElmer. I'm pleased to welcome you to our seminar titled Converting HPLC Methods from Traditional Columns to Solid Core Columns. In this session, you'll learn about superficially porous polymer, or SPP, solid core columns, and how they will improve your productivity and HPLC results. The session will begin with a discussion about the basics of SPP columns, followed by a detailed review of guidelines for migration of both isocratic and gradient HPLC methods to these columns. We will end with a discussion on how to optimize your HPLC system to take full advantage of the powerful capabilities of SPP columns. I want to thank you again for attending our webcast and conclude my remarks with an introduction of our speaker. Dr. Jason Weisenseel is Chromatography Technical Leader for Aftermarket Products at PerkinElmer and Visiting Research Associate at Vanderbilt University. Prior to his current position, he was an LC and LC Mass Spec Product Specialist with PerkinElmer for 3 years. He was a tenured Assistant Professor of Chemistry at the University of North Alabama prior to joining PerkinElmer, where he taught chemical instrumental analysis. He was also previously employed by Daikin America, where he was a Senior Chemist and Quality Control Supervisor. Jason earned a Ph.D. in Chemistry from Vanderbilt University in 2000. And now I'm very pleased to introduce Dr. Jason Weisenseel. Jason?
Thank you, Mike, and thank you, everybody, for attending today. You can type in your questions as the presentation proceeds, and then I'll try to answer as many questions as possible at the end of the presentation. Today's presentation is basically on superficially porous particle columns. A lot of times you'll hear these referred to as solid core or fused core type columns. What we will cover today is basically an introduction to these types of particles for HPLC and their advantages, and then most of the presentation will be on how to migrate a method from a traditional fully porous particle type column to one of these new SPP columns. And then we'll finish up with talk about some advantages of optimizing your HPLC systems for low dead volume in order to get the optimum performance out of the columns. And I'll summarize and then try and answer as many questions as we can. So to begin with, I want to talk a little bit about the advantages of superficially porous particle columns. I'll start with a diagram of a traditional fully porous particle and a superficially porous particle. On the left is a representation of a fully porous silica particle. This is the traditional particles used for most of your HPLC columns used today. The particle size of these started at 10 micron, and then we moved into 5 micron and 3 micron particle sizes, with each progression to a smaller particle giving you higher column efficiency and better separation efficiency on the column. And now the movement has been to what we call sub-2 micron particle sizes. These are smaller particles used in UHPLC systems, ultra-high performance liquid chromatography systems, and the movement there is so that as you go to smaller and smaller particles, you're getting the advantage of higher separation powers or higher efficiency of the columns. One of the disadvantages of using these sub-2 micron UHPLC particles is that they have high back pressure on the columns, so that a lot of times you have to buy new HPLC or UHPLC systems in order to accomplish those high pressures in order to use those columns. Also, those UHPLC systems have optimized dead volume. In other words, they have low dead volume in the system so that you get the optimized separation. The SPP particle, in contrast, uses a solid silica core. They come in different sizes. The size that we use is a 1.7 micron solid core, and then applied to that core is a porous silica layer. And then upon that porous silica layer, as your chemistry is attached and your end capping, such as C18 or say cyano groups, whichever type of column you're using. The advantage of these is they give you a shorter diffusion path through which the analytes have to pass in order to interact with the particle, and you get several advantages in terms of efficiency and back pressure. And so you look at the three key advantages of SPP particle type columns is their high efficient, very fast chromatography. Secondly is reduced back pressure when compared to your sub 2 micron particles, and the ruggedness of the column, which exceeds those of most of the sub 2 micron particle size columns. And so if we look at each of these with more detail, in terms of high efficient fast chromatography, oftentimes when converting from a 5 or a 3 micron particle size column, you can cut your run times as much as 75%. So that time savings gives you an enhancement in productivity. You get nearly twice the efficiency compared to a 3 micron particle size column in terms of separation. And you get equivalent or better, sometimes better efficiency than your sub 2 micron UHPLC columns. And so this ends up with, so what you get is an improvement in productivity, but at the same time, if you're running your chromatograms faster, you're also reducing the mobile phase consumption, the amount of waste that you're generating on a per sample basis. In terms of reduced back pressure, compared to a UHPLC type columns, you usually see about a 40 to 50% reduction in back pressure. The advantage of this is that oftentimes you can perform your analysis with a SPP column on a traditional HPLC system, which goes to 6,000 psi or 400 bar, as opposed to having to buy a UHPLC system that is a high pressure pump in order to utilize the UHPLC columns. And finally, these are very rugged. One of the disadvantages of UHPLC sub 2 micron particle size columns is they often clog very easily, and they tend not to last as long for two reasons. There's a lot of physical stress on the silica itself when you run these at the extreme pressures of, say, over 10 to 15,000 psi. You also get frictional heating, which causes breakdown of the silica faster than you would normally see with silica running below 6,000 psi. In addition to that, since these particles are 2.7 micron total diameter, we can use 2 micron frits at the inlet and the outlet of the column, as opposed to the UHPLC columns, which usually use 0.2 micron frits and are much more likely to clog. So due to less degradation of the silica and the less likelihood of clogging, these tend to be much more rugged than your standard UHPLC type columns. And so as an example of the improvement in efficiency, here's an example of a standard 5 micron particle size, fully porous column compared to an SPP column. This is a chromatogram of a test mix that we use for gradients, but I'm using it in an isocratic mode. If you'll notice that both of these were run isocratically at 60% ACN, 40% water. The flow rate on the 5 micron column was 1.2 mils a minute, which is really the optimum flow rate for that size of column, 4.6 millimeter ID 5 micron column. And you'll notice that this run takes about 18 minutes. The efficiency was calculated based on plates per meter, so that it is independent of the column size. And you'll notice that the efficiency of this column is about 88,000 plates per meter, and that's based on that toluene peak that's highlighted in blue. Excuse me. And then in the bottom chromatogram, we ran this same test mix on a SPP column. The flow rate on this column was 1.8 milliliters per minute, because that is the optimum flow rate for that particular column. But you'll notice that you can run that same mix in about 5 minutes as compared to 18 minutes with the traditional column. And so this represents about a 72% reduction in runtime. And if you look at the efficiency in terms of plate count, you're getting about 23 230,000 plates per meter, which is about a 2.5 times improvement in efficiency compared to the 5-micron particle size column. Also, we compared these to some sub-2 micron particle size columns from a couple of competitors and also one of our own. This is the same test mix. The chromatogram in the top left-hand corner is on the SPP column. It's a 100 millimeter by 2.1 millimeter column. You notice that I get complete separation of all 9 components in less than 6 minutes, and the back pressure on this column is about 3,600 psi. Under the same conditions with our 1.9 micron particle size column in the top right chromatogram, notice I still get complete separation of those in a little over 6 minutes. The plate count's a little higher, so the efficiency is a little higher, but notice the pressure is already at 6,450 psi, which exceeds the back pressure of most of your traditional HPLC systems. And then again, looking at competitor A and B, these have extremely high pressures, although a little bit better plate count and efficiency. Very similar chromatograms, but the key here is that with the SPP column, you can run that at much lower pressure, about 40 to 50% of the pressure of the UHPLC columns, which is going to allow the column to last longer and also put less wear and tear on your system. So next we'll move into a method migration, and I'm going to step through kind of a simple method migration for an isocratic method. This is with a mixture of UV absorbance for sunscreen. And these guidelines are based on a white paper that we have available on converting methods from traditional columns to SPP columns. And after the webinar, we will be sending out emails to each of the participants, and it will have links to not only these guidelines, but a calculator that you'll see later as well. But the general steps for a method migration, there's 6 steps. The first step is you've got to choose an HPLC analysis that is appropriate for migration. And when I say an HPLC analysis that's appropriate for migration, I'll talk in a little bit more detail here in a moment, but basically an analysis that you have a column, an SPP column that would fit that analysis, and also you want to choose analyses that are usually longer so that you can get the maximum payback in terms of the time savings. Second, you've got to define your suitability requirements. In other words, what are my requirements that I want to have in my transferred method in terms of, say, resolution, linearity, limits of quantitation, and so forth. Once you've defined that, then you choose your SPP column, and we have some tools available to choose that column. And then we have some tools for calculating the method parameters, and there's generally 3 method parameters that need to change: the flow rate, the injection volume, and if you're doing a gradient, the gradient time. Then you can run and evaluate the transferred method, and finally optimize and verify your suitability. And so what are good candidates for transfer? Well, in my mind, good candidates would be those that have long run times. Say you have run times of 30, 40 minutes now, you could optimally reduce those to 10 minutes or less. If you have heavy sample loads and you're having difficulty getting through all your samples each day, if you could speed that up, you could be able to get through all those samples on a single system instead of on multiple systems, for instance. You need to choose a method that uses a stationary phase that's available in SPP at this time. Or if you just need improvement in resolution in a current method, you could also use the SPP's higher efficiency in order to improve that resolution. For point number 3, the SPP columns that we currently have available at PerkinElmer are mostly reverse phase with 1 normal phase chemistry. These are all silica-based. We have a C8 and C18, which are kind of your general purpose nonpolar compounds. We have a peptide ES-C18. That's an extra stable bonding with a higher pore size in the silica to accommodate peptides and proteins. We have a pentafluorophenyl and phenylhexyl, which usually give you alternate selectivity for aromatic compounds. We have the RP-amide, which will give you some alternate selectivity for more polar or midpolar and nonpolar compounds. And then we have the helix, which is your normal phase type column. So we had an analysis from a customer, which was the analysis of some sunscreen actives. And the customer is currently running this on a Brownlee validated C18 column, excuse me, and a relatively large column. It's a 220 millimeter by 4.6 5-micron column. On this column, they were able to separate all 6 components in about 14 to 15 minutes. And the critical 3 were the octocrylene, avobenzone, and octinoxate, which are eluting between about 10 to 12 minutes. So this was a good candidate because of the longer run time. It uses a C18 column, which is available in the SPP. And so then we decided to use this as our method for transfer. Next, we wanted to define our suitability requirements for the transferred method. And the basic requirements were first to maintain a resolution of 1.5 or greater between the octocrylene, avobenzone, and octinoxate. Second requirement was to maintain the limits of quantitation or the sensitivity of the method at the current levels or better. The third and fourth requirements were to have linear ranges for all components except for oxybenzone and octinoxate at 100 ppm. Excuse me. And oxybenzone and octinoxate have a linear range to 50 ppm. And then the curve fits, or the R-squared values for the cal curve, should be 3 nines or better. And so to summarize those suitability requirements, basically a resolution of 1.5 or greater for all components, especially octocrylene, avobenzone, and octinoxate. Limits of quantitation should meet or exceed the current limits of quantitation, and we want linear dynamic ranges to match the current method, and R values for the cal curves of 3 nines or better. The next step is to select an SPP column that would meet the requirements of this analysis. Now, I previously mentioned that we have a white paper on conversion of methods that we're going to send out the URL for. For the next few slides, all of these tables and calculations are covered in the white paper, and it takes you through this procedure step by step. The first thing is selecting the right SPP column. Of course, in terms of stationary phase, we were using a C18 before, so we would choose a C18 SPP column. And next is choosing the correct dimensions. One thing to mention on column dimensions, if you're just trying to transfer a method and you want the same resolution, you can use the chart shown here in order to select the correct column length for your particular analysis that will give you the same plate count or better than you're currently using so that you can maintain the same resolution. In terms of column diameters, the SPP columns come in 3 diameters, a 2.1, a 3 millimeter diameter, and a 4.6 millimeter diameter. Generally, if you're doing LCMS, you want to use a 2.1 millimeter ID and maybe sometimes a 3 millimeter ID, but 2.1 is going to give you the appropriate flow rates for a mass spec system. If you're doing UV, PDA, fluorescence analysis for your detector, a 3 millimeter ID column I believe, is the ideal column because it has a lower flow rate and good plate counts, whereas a 4.6 is also appropriate as well. Now, the column we were currently using on this analysis was a 220 by 5 micron column, so I identify that on the 5 micron line of this chart, and then simply extrapolate. back to the 2.7 micron fused core column. And as we see here, the recommended column length for this would be an 80 millimeter column. Since we don't have 80 millimeter columns, we're going to move up to the next size appropriate. And so I chose a 100 millimeter by 3 millimeter column. And then finally, we can calculate, based on relative back pressure of different particle sizes, what the estimated back pressure of that column would be on our system based on the back pressure of the current column. And it's a simple calculation based on the current pressure, the relative pressures of the two columns, and the length of the two columns. And so in the original analysis, the back pressure was around 1600 psi. Using this table and the lengths of the columns, I could estimate that the back pressure on the new column would be around 2500 psi. And it's well within the range of a standard 6000 psi HPLC system, so I could use this column for this analysis on my current system. Finally, and what people fear most, I think, in doing these method conversions is how do I calculate my method parameters for the new column? Well, basically, there's really 2 or 3 parameters that you have to transfer with the new column. One of them is the injection volume. These columns will have, normally will have a little lower capacity than your standard column because you're usually going to a shorter column than you would with your standard fully porous particle size column. And so injection volumes, as a rule, you don't want to exceed 1 to 5% of the column volume. And so the calculation is based on the interstitial volume of the column and the current injection volume. And so it's basically a ratio of the two. In the white paper, we have a table which gives you estimated volumes, column volumes for different size columns, both standard, fully porous, and SPP type columns. If you notice here, for the 220 column, we don't have a 220 column, but we have a 150 and a 250. I took the average of the two, calculated that the interstitial volume of a 220 millimeter column was about 2.3 milliliters. For the SPP 3x100, it's about 0.356. If I then calculate that ratio, excuse me, the estimated new injection volume would be about 1 microliter. There's also an alternative way to calculate this, assuming that they're both fully porous particles, and you could just use the column diameter and the column length to estimate the new injection volume, and you get a pretty similar number, 1.35 microliters. And the reason I mention this alternative calculation is because we have a calculator that's based on fully porous particles that you can use to simplify this process. Next is to calculate the optimum flow rate, or the correct flow rate for your new column. And most columns will have an optimum flow rate for the best resolution on that column. If you look at SPP columns, the optimum velocity on an SPP column is about 0.3 to 0.4 centimeters per second. Now you can convert that to flow rate based on the column internal diameter. But really a good rule of thumb for SPP columns is that for a 2.1 millimeter ID column, the optimum flow rate is usually about 0.4 to 0.5 mils a minute. For a 3 millimeter ID column, optimum flow rate is usually around 1 mil a minute, 0.8 to 1.2, I would say, is the range. And for a 4.6 millimeter ID, it's 1.8 to 2.3 mils a minute. And as you can see from these flow rates, that's why I mentioned earlier that the 2.1 millimeter ID column is really optimum for LCMS, because those lower flow rates are usually better for electrospray ionization in the mass spectrometry portion of LCMS. But in the white paper, we also have a table which gives you optimum flow rates based on column diameter and mobile phase velocity. And so for a 3 micron or 3 millimeter ID column, that optimum flow rate is about 0.8 to 1.1 mils per minute. Again, I have an alternative calculation in which you can take into account the column diameter and the particle size. And taking ratios of those, you can calculate the optimum flow rate based on your current flow rate. And so the flow rate on the current column was 1 mil a minute. For the new SPP column, the estimated flow rate would be 0.79 mils per minute. And so it's pretty similar to the using the table as well. And so finally, really the only parameters I had to change in this method, if you look in the center column, those are the parameters for the current column, the 5 micron column. I'm using 14% water, which contains 1.25% acetic acid and 86% acetonitrile. It's an isocratic. It's an isocratic run with a flow rate of 1 mil a minute, a 7 microliter injection, and we're sampling at 5 points per second. One thing, when you go to faster chromatography, you will have to increase the sampling rate of your detectors as well. Generally, for the SPP columns, I find that 10 to 20 points per second is more than ample in terms of sampling rate. And so if you look at the new method, really all that changed was the flow rate went down to 0.8 mils a minute, and I'm going to change the injection volume to 1 microliter, and I'm going to increase the sampling rate. As mentioned earlier, we also have this calculator, which will send you the URL in order to download this later, which was actually used for sub-2 micron UHPLC particles, but it works just as well for SPP. And these were all the alternative equations. This spreadsheet is based on the alternative equations. But the nice thing about this spreadsheet is on the left, you can put in your current column dimensions, your flow rate, your resolution, and your injection volume. And on the right, you put in the dimensions of your new SPP column, and it'll automatically calculate the flow rate, the injection volume, and if you're doing a gradient, it will calculate the gradient. It'll also give you an estimate of the savings in terms of mobile phase and time. And finally, once we have all our parameters set, we would run and evaluate the transferred method. And so this is the new method. If you remember, previously we were running this in about 14 minutes. We still maintain that resolution of 1.5 or better between the octocrylene, avobenzone, and octinoxate. And if you look at the comparison of the two chromatograms are very similar. You'll notice the avobenzone position in relative to the octocrylene and octinoxate is a little bit shifted to a shorter retention time, but the time savings is enormous. You're looking at a 16-minute run going down to under 3 minutes with the same resolution or better. And so I tried to optimize this a little bit to try and center that avobenzone peak between the octinoxate and octosalate. And so basically I adjusted the mobile phase composition slightly. It was at 14% aqueous before. Now it's at 12% aqueous, and I also increased the injection volume in order to meet my limits of quantitation. But some slight modifications, and now I have a chromatogram where the avobenzone is almost equally between, or equal time between, the octocrylene and the octinoxate. If we look at our suitability requirements, I've met the resolution requirement of 1.5 or greater. I've also met the limits of quantitation. In fact, they got a little better with the SPP column. And just to demonstrate that the LOQs are met, these are some samples that were run, or some injections that were run just above the limit of quantitation to demonstrate that you can still see the peaks at a signal-to-noise ratio of 10 or better. And for all components, we were still able to keep the same dynamic range of up to 100 ppm and keep the R values at 0.9 or 9 or 3 nines or better. And so if you assume that this method was run in the lab 5 days a week, 8 hours a day, on that 5 micron particle size column, you could get about 125 samples run or injections per week. Now with the SPP column, where you're running below 3 minutes, you can now get that same number of injections in about 7 hours. And so that you can do the same amount of work that used to take you 5 days now in a single day. And that constitutes about a 550% improvement in productivity. In addition, if you look at cost savings, I just did a simple calculation based on what I pay today for my solvents. I have on the 5 micron particle size columns on a per year basis for acetonitrile water and acetic acid, I would pay about close to $9,500 a year for those mobile phases. On the SPP column for the same number of injections, I would say my solvents would cost about $1,400. And so this constitutes about an 85% savings in mobile phase. And that's a significant savings. And that does not take into consideration either the disposal of your chemicals. Oftentimes it costs more to dispose of the chemicals than it does to purchase them originally. And so as you can see, with a simple isocratic method, the basic steps are, once you've chosen the method that you want to transfer, is to determine the correct column. And once you determine the correct column, you can use the calculator or the white paper to calculate your new injection volumes and flow rates. And then it's simply a matter of changing those parameters on your LC system, running some test injections, and then optimizing for that particular sample. So next we'll talk a little bit about using a gradient method as opposed to an isocratic method. And it's the same procedure as before. First you would choose, the correct method and then the correct column, and then calculate your new parameters, and you can use the calculator to do that, and then finally optimization. And so for this example, I use that same gradient test mix that I talked about in the previous slides when I was talking about column efficiency. This first slide represents the separation of that gradient test mix on a 150 by 4.6 millimeter 5 micron column. I ran this at a flow rate of 1 mil a minute, and it takes about 15 minutes for the gradient. The gradient here is represented by the dashed red line, and that's in percent of acetonitrile. So basically the gradient starts at 50% acetonitrile, and then moves to 90% acetonitrile, and then returns back to 50%. Again, the first step is column selection. I would use a C18 column. I can extrapolate from this chart from the 5 micron by 150 millimeter column to the SPP column. And the recommended column here would be a 60 millimeter column length. Since we only have a 50 or a 75 millimeter column length, I always want to move up to a longer column, so I chose a 75 millimeter column. And again, I calculate the back pressure that would be expected for that particular column. And so in the original method, the maximum back pressure was about 2,800 psi. Now with the new method, it's at 46 or 4,700 psi, which is still well within the range of a 6,000 psi system. This time, instead of going through all the individual calculations, excuse me, I used the calculator. And with the calculator, I plugged in on the left-hand side the dimensions, the flow rate, and the injection volume of my current column. Also, if you look in the bottom left-hand corner there's a table where you could input the values or the times and composition of your gradient. And then on the right, you put in the dimensions of your new column, and it will automatically calculate your new flow rate, injection volume, and your gradient. So I took these parameters and ran the new gradient, and notice that now what was done in about 14 minutes is done in 4 minutes. I get the same retention order of my compounds, but I get to do them in about 75% of the time. And so here's a comparison of the initial gradient program with the 150 millimeter column, and that's a 14-minute run. And finally, the new gradient with the SPP column, which is now about a 3-minute run. Now, one of the things that you got to consider when you are using SPP columns is you may need to optimize your HPLC system. And so in the next couple slides, I just want to talk a little bit about optimization, and then I'll finish up with a short summary and then open up the floor for questions. And so there are some considerations you got to think about when using solid core SPP type columns. First, in most cases, you will keep your injection volumes low. The capacity of these, since they are not a fully porous particle, will be lower than your traditional columns, and so that you will need to usually go to lower injection volumes. Now, that's not always the case. It does depend on the concentration of your sample originally. If you have a very low concentration sample, you can go to larger injection volumes. But when you do that, you want to make sure that the solvent you're using for your sample is weaker than your mobile phase on your column. In other words, say I'm using a 50-50 mixture of ACN water as my isocratic mobile phase. I would want to dissolve my sample in 50-50 ACN water or in more water, say 75% water, 25% ACN, so that's a weaker mobile phase than, or a weaker sample solvent than the mobile phase. And the reason for this, if you use a strong solvent such as ACN and you do a large injection, what's going to happen is you're not going to get good retention of your analytes on the column, because as that plug of 100% ACN moves through the column, it's going to carry with it your analytes. The other thing is, and I mentioned this earlier, is using faster detectors. Usually sampling rates of about 10 hertz or even 20 hertz are ample for most of these analyses. If you get into like a sub 1 minute analysis, you might even have to go to a higher sampling rate, but generally that's not the case. Most people are running things in 2 to 3 minutes or more. But really, what's important here is if you're going to use these columns on an older system, you may need to optimize your current system in order to reduce the dead volume. Because if the system has large diameter tubing or a large flow cell, or even a large loop in the autosampler, these cause dispersion of your peaks as they pass through the LC system. And so if that system causes too much dispersion, what you're going to see is overlap of your peaks. So to optimize a system, it's really basically 3 things that you can optimize on your system. The first thing to do is to use smaller internal diameter tubing. Some of your older systems will have 0.007 or 0.010 inch ID tubing running from the injector to the column and from the column to the flow cell. Those are the 2 critical pieces of tubing that you have to replace. If you take those and replace them with .005 or .004 inch ID, or in some cases you can even go to a .0025 inch ID, if you go to a smaller ID tubing, you're going to eliminate dispersion and what we call dead volume in your system, and you're going to get sharper peaks. Second thing you can do is you can use a smaller loop volume in the injector. In the smaller loop volume, I would use a 10 or a 20 microliter loop as opposed to, say, a 200 microliter loop. And then finally, probably, and one of the most important things, is to get low volume flow cells for your detectors. Older flow cells and older detectors will have very high dead volume, say 15, 20, even 30 microliters. You want to reduce that dead volume by buying a more high efficient, lower dead volume flow cell. Now we offer kits for these, for our FlexR systems, for the Agilent 1100 systems, and also for the Shimadzu systems, which will be coming out soon. Not only do we offer these kits, but our service engineers can come in and install those kits if you're not comfortable with installing those kits. But let's look at the next slide, and it'll give you an example of how optimization of your system can improve your chromatography. Here are two chromatograms, one in which one was run on I have an old Series 200 PerkinElmer system here in my lab. The traditional configuration of that system was .007 inch ID tubing from the injector to the flow cell, and from the flow cell, or from the injector to the column, and from the column to the flow cell. Also, it uses a 200 microliter loop in the autosampler, and the flow cell itself is a 10 millimeter path length, 15 microliter flow cell. So I ran the same test mix that I used in all the previous slides. You'll notice I get separation of all 9 components, but if you look at the two, the second and third eluting components, the ethyl 4-hydroxybenzoate and the dimethyl phthalate, you'll notice that those are not baseline resolved. They're eluting at like 0.4 and 0.5 minutes, respectively. Now, under these same exact conditions of flow rate, mobile phase composition, and injection volume, I ran this same SPP column, but I optimized that HPLC system. Basically, what I did was I replaced the loop in the autosampler with a 20 microliter loop. I used .005 and .004 inch ID tubing, and I used our high efficiency 6 millimeter by 2.4 microliter flow cell. And if you look at the bottom chromatogram, that was run on the same system, but now notice the improvement in resolution especially between the ethyl 4-hydroxybenzoate and the dimethyl phthalate. Now you also look at the efficiency of each of the columns, which is listed on the right. The efficiency of the system in the column for the first chromatogram was about 72,000 plates per meter. And then for the optimized system, you get about double the efficiency. And all that efficiency comes just from optimizing the system, not from the column itself, because we're using the same column in both of these chromatograms. So as you can see, optimization, if you have some critical pairs of peaks, optimization can be a major advantage when using these new fast, high-efficiency SPP columns. Finally, just to let you know what we have available for SPP columns, we have a variety of reverse phases. We have C18 and C8, where C18 is probably the most commonly used general purpose column for nonpolar to midpolar compounds in a polar matrix. C8 is just a shorter ligand chain, which will give you a little less retention. So if you have highly nonpolar compounds, you would use a C8 versus a C18 because you have a little less retention and they'll come off the column a little easier. You have an RPA amide for more of your midpolar to polar compounds. This has an embedded amide group in a C18, and it's an end cap type particle. We have the pentafluoropropyl and the phenylhexyl, which are appropriate a lot of times for your aromatic compounds. And then, as I mentioned earlier, the ES peptide, which is a C18, but the silica particle itself has a higher porosity or larger diameter pores, which allow the penetration of the peptides and proteins into the particle so that you get maximum interaction and separation of peptides. We also have helix phase, which is basically bare silica, which can be used for your normal phase chromatography. So if you're trying to isolate very polar compounds in a nonpolar matrix, the helix phase works very well for that. The columns, in terms of sizes, come in several different diameters, or 3 different diameters, 2.1, 3.0, and 4.6 millimeter ID. As I mentioned earlier, the 2.1 millimeter ID is the best for LCMS, and then I like the 3.0 and the 4.6 for things like fluorescence detectors and UV detectors. Column lengths come in a variety from 20 millimeter column lengths to 150 millimeter column lengths. And the other advantage of these when compared to UHPLC columns is if you need very high resolution, and because of the lower back pressure, oftentimes you can couple 2 columns together, say 200 millimeter columns with a zero dead volume connector or 250s to get a very long column that you can run on a higher pressure system and get the ultimate in resolution of your compounds. This a lot of times is not doable with the UHPLC columns, because when you start to couple multiple columns together, you're going to exceed the back pressure of even your high pressure systems that run at 15 to 18,000 psi. And so that's a major advantage of the SPP columns. We have guard cartridges in all the phases mentioned above, C8, C18, RPA amide, and so forth. And they come in the 3 different diameters based on the column diameter that you're using. We have a special holder for those, which is a cartridge type holder with a high pressure fitting that is finger tight. And then finally we have the system optimization kits that I mentioned earlier. We have the PerkinElmer series for the Series 200, the FlexR. We also have complete optimization kits for the Agilent 1100 HPLCs, and we have others coming soon. And so I'd like to summarize by saying that really the keys to success in terms of method migration is proper planning. So those first few steps of that migration where I talked about choosing the right HPLC analysis and then choosing the column and the right column dimensions, those steps are key in a successful migration. Because if you choose the wrong column that's going to give you too high a back pressure, you're just going to be frustrated by the fact that you're not able to use that column at its optimum flow rate to get the maximum efficiency out of the column. And so those are kind of key to your success. Once you have the right column and you've chosen the right analyses, the tools that we have available make the conversion of the conditions pretty simple and pretty straightforward. Also, optimization is usually pretty rapid because now your run times are much shorter. A lot of times in HPLC method development, it's a very long, tedious process because you have very long run times, say 30 to 60 minutes. You have to make one change, test it, make another change, test it, which makes the method development process very slow. When you're using fast columns, method development goes much faster, and so that you can get that method optimized in a very short period of time. And remember that the key here is that you can increase your productivity by 75% or more by decreasing your run times. You're going to decrease the consumption of your mobile phases as well on a per sample basis, because you're usually going to use slightly lower flow rates and shorter run times, and you'll also lower your disposal costs. And don't forget that if you need them, we have HPLC optimization kits available for many systems, and if you don't have, if it's a system that we don't have on our list, we can definitely recommend the parts that you need in order to optimize your current system. And our service team, OneSource, can come in and install those optimization kits if you don't feel comfortable with installing yourself, or they come with the instructions so that you can do it yourself. And so with that, I'll conclude, and I'll thank you for your attention today, and I'll be happy to take any questions. First question comes from Julie. Her question is, let's say I already have a new UHPLC system and I've tried the sub 2 micron columns. I'm not happy with the lifetime of my columns. Can SPP still help me, and can I still use the calculator? Yes, Julie, of course. One thing is the SPP columns are going to last a lot longer than the sub 2 micron particle size columns. I've done some studies here in this lab where I've gotten over 3,000 to 4,000 injections on a single column. And so that'll definitely help improve your lifetimes. Of course, you always want to be careful to make sure that you filter your samples carefully and filter your mobile phases. And you can still use the calculator. The calculator is independent of the system you have. And so all you need to do is get the calculator and have an SPP system. Next question I had was concerning the low volume flow cell. The question is that to optimize your system, you have to use a lower volume flow cell, and it has a shorter path length. Wouldn't that not decrease your limit of quantitation or your sensitivity of your system? Well, I flipped back to this slide shown here. And if you'll notice, before and after on that optimized system, I used a 10 millimeter path length flow cell in the unoptimized, non-optimized systems in the top chromatogram, and a 6 millimeter path length flow cell in the optimized system. Well, you don't get a loss in sensitivity because your peaks are much sharper and taller. So what happens is with the 10 millimeter path length flow cell and go into a 6 millimeter, according to Beer's law, you would assume that you would get a 40% reduction in absorbance just based on the path length. Well, that is true, but because when you optimize your system and you go to the narrower ID tubing and the lower volume flow cell, your peaks become sharper and taller, and so really it kind of washes out. And if you look at these two chromatograms, you get kind of the same sensitivity pretty much between the two, and the reason is for the height and the sharpness of the peaks. Well, I think there are no more questions. Of course, you can always submit questions later through your registration, and you should be receiving an email next week with links to the conversion calculator and the white paper that I mentioned for converting methods. I guess the point here is that, don't be scared to convert methods. It's not as hard or difficult as you would think they are. And the columns themselves and the short run times will save you, a lot of money and improve your productivity as well. With that, I'd like to thank you for your attention and have a good day.